Now let's talk about best, worst, and average cases. So as you can guess from the title, so we need to find out what is the best case and worst case and average case of certain algorithm. So I have 7 slots here. So it can be a list, it can be array, whatever, some other certain linear structure. And what we want to do, we want to find a target by using linear search or sequential search. So when you try to find certain target, certain number, certain item in the linear structure, and how we search it. So simply what we do is check the first one and check the second one, check the third one, check the fourth, and we just do it until we find the target, right? So that case, let's say, if our target is 1, then how many steps we need to perform? 1. But if our target is 7, then how many steps we need to do? 7 steps, right? But if our target is some arbitrary or random number, it can be 3, it can be 5, right? So then let's think about it. Then what would be the best case of linear search or sequential search? The best case would be 1, the first one, right? So it takes only 1 step. It means big O 1 or big theta 1, right? And worst case, the 7, right? Also, that is n, the problem size, or big theta n. And what would be the average case? It can be 2, 3, 4, 5, 6. So that case also we use that, we just treat it as n, big O n or big theta n, right? So that's the best, worst, and average case of linear or sequential search, right? Then for sequential search, the best case occurs when the algorithm is implemented efficiently. The search target is near the front of the array. The search key is small. The array is small. So what's the answer? Answer is B, because as we just tried, when search target, if it is located in the beginning or the front of the array, then that's our best case. Then the worst case for sequential search occurs when the last element of the array is the value being searched for. That is true or false? Again, think about this case. Yes, it is true because we already tried it. Next question, the best case of in the best case, a sequential search is, of course, it's B because it requires only 1 step. We already checked it out, right? And faster computer or faster algorithm. So this is a good question that you can think of. So I say, my students, you will not experience most cases your better algorithm and worse algorithm. It is really hard to tell the difference between better algorithm and the worst algorithm for this class or for your own program or for your like programming assignments, whatever case. And simply why? Because your problem size n is small and your computer is pretty powerful enough. So if you think about your problem size, maybe there might be like 100 or 1,000, even 100,000 entries. But how about how many computation your CPU can do per second? If you think about your CPU power, and if you think about your problem size, then it's really hard to check the difference between the better algorithm or worse algorithm. But if you get a job in the field and if you start dealing with real real world situation, the problem size, then you will see, oh, it's not about the computing power, but the important one is the algorithm. And when you try to deal with the real world situation, you will think about how I can save memory, or how I can reduce this computation as like cycles. It means like uh, n square, like it means like a nested loop that is really bad. But your case, for example, if you have like 10 uh, if your problem size is 10 or 100 and one is like n square big O or big theta n square, another one is big O n, and algorithm wise this one is significantly worse than this one, right? But if you tried like 10 problem size, that is 100 and this is 10, of course this is 10 times slower, but empirically, your CPU is really fast, so it's really hard to tell the difference. And maybe there is like a second, even a 1 second difference that can be huge, but you cannot notice the difference because it takes only a 1 second difference. But if you starting having the real world situation problem size, it can be 1 million, right? Then that can make a pretty big difference between this better and worse algorithm. So of course, the fast computer is important, but more important one is the faster, more efficient algorithm. And this one is a good example. So consider an algorithm that contains loops of the form. So here is one loop, another loop, and another 10 times of iteration. So if task T requires T time unit, the innermost loop on Z requires how many time unit? So that is T requires T, then how many iterations it does? 10 times. So 10 T, that is 10 T. So innermost loop, it requires that amount of time. Then here is something else. You need to, if you are not comfortable with queue or stack or other linear structure, then it is good time to review your programming two textbooks, because we will talk about the queues and stacks a lot in linear structure section. So it's a good time to review your previous programming textbook. So in a queue, items can be added. So queue has this kind of, we usually use this kind of example. It goes and it outs, right? So in a queue, items can be added only at the back of the queue. So when we have this queue structure, we put things here. We call the rear part, right? Only at the back of the queue. And operation on a queue can be carried out at where? Again, we put it here and the item comes out here. So the answer is both is front and back. So if you don't get this one, then I seriously encourage you to check out Programming 2 textbook. And if an algorithm requires 2n cube plus 17n square plus 54n plus 512 operations to perform, where n is the size of the input data, then we say the order of the algorithm is what? So I know some of you already learned Big O from your Programming 2 course, but just in case you didn't learn it. So what we talked about the problem, the n size is a big deal, right? So for example, if you have nested loop, and if there is only one nested loop, and if you have like multiple loops, let's say we have 3 loops here. So you might say, well, that is n square, and that is 3n. Oh, then this one is a bad algorithm, you might think, right? Because when I have n is 1, that is 1, also that is 3, and is 2, that is 4, and that is 6, right? And now n is 9, and that is 9. So until I reach n is 3, until that case, this one is a bad algorithm. That is true because n, your problem size is really small. But when we talk about all this algorithm analysis, what we really concern is the big size of n. So that's why when we have these operations, we concern about the higher order. Higher order means like n cube. N cube is higher order than n square. N square is higher order than n. And also we just don't care about the constant. So because, I mean, you might think like, why? I mean, n square is it can be a pretty good deal. But when you compare n square and n cube and n square, and if n is 1, then that will be same, right? And n is 2, that is a small different. But if you increase like 1 million, then that would be pretty big difference, right? So when we analyze algorithms, we concern about only the highest order. So that's why we use n cube, big O n cube. We say that we just drop the constant, and this is lower, it's not the highest order. So that's why we only think about the n. And consider the following nested loop. What is the order of the algorithm? So that is n times, and that is like constant, right? So what we said, we don't care about constant. So we don't count this one. Then n times and n times, that is big O n square, right? If it is not 100, if it is n, then it will be n cube, but this is constant. So how many operations it will do? Like 100 n square, but as we said, we don't care about the constant, so we just drop this one. So algorithm efficiency is typically a concern for small problems only, large problems only, medium-sized problems only, problems of all size. So what's the answer for this one? As I said, large problems only. We don't concern about the when n is 1, when there is only one like a problem size. So we concern about the large problems only. So this one is important. And that's the end of algorithm analysis section.